I wanted to give you an example of using the binomial distribution. So what's the probability of throwing 1 6 on 6 throws of a die? So the probability of getting a 6 is 1 over 6, the probability of not getting a 6 is 5 over 6, and the number of ways that you can get a 6 across 6 die is 6. You can get a 6 on the first die, second, third, fourth, fifth, sixth. So the total probability is worked out like this. So it's 6, the number of ways that you can get it, multiplied by the probability that you get a 6, which is 1 over 6 to the power 1, because you're just looking for 1 6 on those 6 dice, multiplied by 5 over 6 to the power 5, which equals 0.401877572. You would calculate this using the binomial distribution function within Excel. So you type into the cell equals binom.dist, open brackets 1, that's the number of successful trials, comma 6 out of 6 attempted trials, comma 1/6, which is the probability of success, comma false, meaning that you want to calculate the probability just for that number and not the cumulative probability of 1 or 0 6s. Now, let's consider another example in terms of gender. So I have a class of 65 students and 4 of them are male. This actually occurred a few years ago when I was teaching postgraduate class, and I had 4 men and 65 women. So what's the probability that this class is a random sample from the population if the population of genders are equally distributed? So the probability of having a man and a woman within the class is equal. So here I've said probability of male equals 0.5, probability of not male is 0.5. What's the probability of 4 men in 65? So you have to calculate 65C4, choose 4, using, this is definitely using your calculator, of which there are 677,040 different ways of arranging 4 men out of 65. I then multiply that by 1 over half to the power 4, that's the probability of 4 men turning up, multiplied by 1 over 1 half to the 61, which is the probability of 61 women turning up. When you multiply that all out together, you end up with 1.835 times 10 to the minus 14. That is an extremely small number. It's very unlikely that you're going to get 4 men out of 65 students. And you put that into Excel by doing equals binom.dist, open brackets 4 for the number of men, the number of successes, comma 65, the number of trials, probability is a half, and again you put in false. So this is a plot of the binomial distribution for p equals 0.5 and 65 trials. So you can see that most of the time you're going to have a class which has maybe 28 to 32 of one gender compared to the other out of 65. And once you get beyond a skew of 20 to 45, the probability of it occurring is extremely small. So this allows us to calculate if something is unexpected. What you can calculate is what's the probability of something at least as strange as this occurring. So in the case of the men, that would be 4, 3, 2, 1 or 0 men occurring out of 65. So to do that summation, I would do exactly the same sort of calculation as you do in Excel before, but instead of putting false, you put true. So then you end up with a red area on a probability density function. Instead of just having how much probability there is in a single one of the columns, you have how much there is cumulative in the tail. So this was the point of doing the exercises in human height on cumulative probabilities, and also testing you on the probability for a single range within a histogram. As you can see, this is the cumulative distribution function for the set of data. So it looks like an S. Most of the data occurs between 9 and 11 successes for 20 trials and a P of 0.5. So to calculate this in Excel, you go equals binom.dist, number of successes, no successful trials, number of trials, the probability, and you want its cumulative to be now true and not false. So if you put in false, you just get the value for 4 of them occurring rather than 4 or less. You can calculate it in SPSS, but I would suggest that you don't. And you can calculate it in R using the function which says p binom, and the format is very similar to that for Excel. You put in 4, the number of successful trials, you put 65, the number of trials you've carried out, and 0.5, the probability. In R, you do not have to specify true or false for whether it's that particular bin of the histogram. It automatically just sums the tails. So that means that if I have a sample of 4 men and 61 women, then the probability of this occurring by chance is very close to 0. It's 1.96 times 10 to the minus 14. So this would tell you that there is no chance that those probabilities of there being a 0.5 probability of being male and 0.5 probability of being female are true. Something else is happening. My class is not randomly distributed evenly between the two genders. I've disproved that to a very high level of confidence. So this gives me the point of confidence. Probabilities can be expressed as percentages, but I would prefer if you don't do them as percentages. That's because when we're doing the calculations in the tests, they are recorded as decimals. It's much better if you have confidence as a percentage and significance or p-values as decimals. They are interchangeable in terms of thought and where they're derived from, but if you use them in this way, then you won't get confused about confidence and probability. Sometimes I will slip up and say there's a certain percentage chance of something, but try not to make the same mistakes.